Hello everyone. Today I'm going to show you a linear regulated power supply. There are mainly two types of regulated power supplies. One is linear regulated supply and another one is switched mode power supply. So today I'm going to confine my discussion within the linear regulated power supply. I built two types of power supplies. One uses only discrete components and the other one uses an opamp as well. So I'm going to compare the performances of the two. And though linear power supplies are simple, but it has major drawback. That is, it consumes huge amount of power, and that varies under various circumstances. On the other hand, switched mode power supplies are highly efficient. Though linear supplies are not that efficient, but in many cases, it is very convenient to use. As for example, like you are using very little power at the output. So in those cases, in this kind of cases, it is better to use a linear regulator supply. All types of regulated power supply need a reference voltage source. A voltage source whose voltage remains constant over time. Long time ago, mercury cells were used as reference voltage sources. The voltage is around 1.02 volt and is very stable. Nowadays, this kind of mercury cells are replaced by semiconductor devices. There are several sources of reference voltage that we can consider. Any p-n junction diode, a Zener diode, and a precision shunt regulator. The last one is most widely used nowadays. For a p-n junction diode, it is forward biased. Voltage across it will be around 0.6 volt, but it will vary a little with current. The term dynamic resistance comes this point, which is the ratio of change in voltage to the change in current beyond 0.6 volt. This value we want as little as possible. For a Zener diode, the dynamic resistance is less than the normal diode, and for a precision shunt regulator, this value is very, very low. That is why these days this type of shunt regulators are widely used. I'll be using a precision shunt regulator AZ431L. The voltage is adjustable from 1.24 to 18 volt, and its temperature deviation is very small, and the dynamic resistance is only 0.05 ohm. I shorted the adjust or ADG point with the cathode so that it gives 1.24 volt all the time. I use this circuit to test how well the reference voltage source is. I varied the voltage from 1 to 15 volt. Current changes from 0 to 90 milliampere. However, the voltage remains the same 1.24 volt throughout the entire range. In a linear regulated power supply, along with the reference voltage, we need an error amplifier and a pass transistor. The error amplifier compares the difference between the reference voltage and the output voltage and controls the current flow to the base of the pass transistor. If the voltage tries to go high, current IB goes down and vice versa. This arrangement always maintains the output voltage at the reference voltage. Now, if we use a potentiometer at the output as shown in the circuit diagram, we can adjust our desired output voltage and that output voltage will be regulated under various circumstances. Now, for a regulated power supply, we have to consider some voltage drop, like the base emitter voltage drop VBE. It is around 0.6 volt and does not vary much throughout its entire operating range. The collector emitter minimum voltage drop varies from 0.5 to 1 volt depending on the load current. These voltage drops are associated with the very basic characteristics of a transistor. If we take a closer look at the base emitter characteristic, we can see that the voltage drop is around 0.6 volt, and it is increased a little with increasing base emitter current. However, with the increasing base current, the power dissipation of the transistor increases, so does the temperature of the device, which brings down this voltage drop. So we may consider this drop to be 0.6 volt. The output characteristics or the collector emitter characteristics is shown here. Higher the base current, the higher the collector current, and VCE also changes a little. And this minimum drop we may consider 0.5 to 1 volt. This slide shows a simple representation of the transistor circuit. In a linear power supply, the pass transistor acts as a variable resistor if the output voltage tries to change from the set voltage. The base current regulates the collector current. The voltage drop across the collector emitter changes, which tries to maintain the output voltage at the set voltage. As a resistor dissipates power as heat, the transistor also does the same. The amount of power dissipation is simply VCE multiplied by the load current or emitter current. An example is shown in this slide. Suppose we wish to have a fixed voltage 5 volt at the output. We are changing the load from 2 ohm to 100 ohm, and we are using a 12 volt power supply at the input. As the voltage is fixed, the current should change from 2.5 amp to 0.05 amp. The voltage drop across the collector emitter should be 12 volt minus 5 volt, that is 7 volt, and the power dissipation varies from 17.5 watt to 0.35 watt throughout this the change in the output load. The DC voltage sources which are to be used in the input side of the regulator are not ideal, which means all sources should have some internal resistances, which put some restrictions on the ranges of the regulated voltage. As the load current increases, due to increased current, the voltage drop across the internal resistance increases. As we know that there should be at least a 1 volt should be allowed across the collector emitter circuit, the overall range of regulation is thus decreased. Considering the internal resistance to be 5 ohm and the regulated output voltage to be 5 volt, a plot is done using the equations of the previous slides. The blue line represents the regulator input voltage. You can see as the load current increases, the input voltage decreases due to the drop in the internal resistance. For a load current of 1.2 amp, the input voltage is around 6 volt. Beyond that, we cannot draw any more current, otherwise the control will lose on regulation. The power dissipation is shown by the red line. You can see that the maximum dissipation is around 700 milliamp. A simple practical voltage regulator circuit is shown here. This transistor is acting as an error amplifier and the other one is serving as a pass transistor. The reference voltage is 1.24 volt set by the shunt regulator. A fraction of the output voltage to be compared is set by the 5 kilo potentiometer. If the voltage at this base tries to increase more than 1.75 volt, the collector current IC2 will increase and the base current IB will be decreased as a result. As a result, the output voltage will go down until the voltage at this point comes back to 1.75 volt. This is the photo of the implemented circuit. A test setup is shown here with two voltmeter connected on the input and output side. A 47 ohm load resistance is used at the output. The output voltage was set at 5 volt and the input voltage was varied from 5 to 24 volt. The plot for the output voltage is shown here. From 6 volt onward, the output voltage increased by little amount, as you can see, as discussed before. Below the 6 volt input voltage, the control is lost due to the basic requirement that the input voltage should be higher than the output voltage plus 1 volt. I tried another circuit. This time the transistor error amplifier was replaced with an opamp. As this opamp cannot deliver much output current, I used a Darlington pair as a pass transistor whose current gain is much higher than a single transistor. This circuit is implemented on a breadboard. A heatsink is also used with the pass transistor, as higher power dissipation will increase the temperature of this device. This circuit was similarly tested for the output voltage regulation. You can see the output voltage remains firmly set at 5 volt despite the wide input voltage change. Higher gain of the op-amp makes it possible. Another important test for a regulated power supply is load regulation test by varying the load connected at the output and measuring the voltage. Back in the old days, people used to use high power variable resistor called rheostat. These are bulky and expensive. Instead, we can use a simple active load implemented with a transistor and a low power potentiometer. So with this active load, for a change of 1 kilo to 5 kilo of this potentiometer, we can get 1 ohm to 250 ohm at the output. Setting the output voltage at 5 volt and keeping the input voltage at 10 volt, the load was varied and the output voltage and current was measured. As you can see, the voltage goes down from 5 volt to 4.3 volt for a variation of 10 milliampere to 3 amp. We can get similar result using simulation. As before, I am using LT-Spice for simulation. As the SPICE models for the used op-amp and the transistor were not available in the library, I took some close approximation. OP777 for the op-amp and ZTX1048 for the pass transistor. The voltage regulation is shown with the source whose internal resistance is 5 ohm. I get pretty much similar result practically. This slide shows both the input and output voltage. As you can see, the regulation is lost at around 630 milliampere. The input voltage is around 6 volt. So beyond 6 volt, the regulation is lost. This slide shows the power dissipation. You can see the dissipation goes up and then goes down. So far I have not talked anything about using capacitors in the circuit. Of course, for a practical circuit we need to add some filter capacitors for better performance. The filter capacitors will reduce the output ripple. This slide shows where we should place some filter capacitors: input, output, and on the reference voltage source. For an input voltage source of a regulator, we can use a transformer rectifier circuit as shown, or we can use AC to DC switched mode power supply. I am trying to test the precision shunt regulator circuit. So this is the breadboard and the shunt regulator is shown here. This is AZ431L. I use two resistors in series to limit the current below 100 milliampere, and two voltmeters were used. One is for measuring the input voltage and another one the output voltage. As you can see, I am increasing the input voltage and the output voltage remains almost constant at 1.24 volt. So now you can see almost 7 volt input voltage and output remains the same. It's still going up, the input voltage, and no change so far at the output voltage. So now it is 10.2823 and it is still going up. So, and that is the output voltage remains at 1.24, around 1.24, and is not varying much. So now this is the regulated power supply, and I am using the input voltage around 10 volt and the output voltage I can vary with this potentiometer. A 47 ohm load is connected at the output. You can see as the potentiometer is changed, the output voltage is changing, and I wish to keep it at 5 volt. So as you can see that the voltage at the output is going up, and then I'll take it down to 5 volt. So almost at the 5 volt, and input voltage is 10.25. And now I am trying to increase or decrease the power supply, the input power supply voltage. You can see that as the voltage going up, the output voltage goes up a little, and as it is going down, the output voltage also goes down a little. So beyond 6 volt, you can see the voltage drop. The voltage, output voltage, will go down rapidly because it will lose total control of the regulation, and it is back to 5 volt at 10 volt input voltage. Now you can see I am using the different power supply, that is the power supply with an opamp. So with the increasing or decreasing voltage, the output voltage varies very little. You can see now 9.6, 10, 11, 12, and output voltage remains the same at 5 volt. So it is way more stable than the previous one. That is, the supply with the transistor is less stable compared to the power supply with the opamp. Now I am varying the output voltage. So keeping the input voltage 10.2 volt and I am increasing and decreasing the output voltage. So now I am going to use the load test with the power supply. So the active load is connected, and as you can see, I am measuring the output voltage and output current. As the current goes up, the voltage is going down. So at 1 ampere current, just 4.7 or something voltage. So the current going up and the voltage is going down. So at 3 volt, it is kind of going down a lot. So this shows the input side of the regulator. The voltage remains fixed at 10 volt, but the input current is going up. It has a limitation of up to 3 amp, so I cannot go beyond that.